Rahul Prabhune, and I wanted to walk you through my deep learning project for credit card fraud detection. So the goal of this is to find whether a transaction is a fraud or non-fraud. The matrix that we are looking at is whether what is the F1 score at the end of the day. So we want the score to be at least more than zero point 0.84, and I'm running this on my local machine over here with GPUs. And the architecture that I'm following right now for this is a diverse model for XGBoost, which is tree-based, and then TabNet, which is the latest model out there. There was a paper uh, published by Google in 2020 on this, so this is pretty new on the attention-based deep tabular network. And then we have a multi-layer perceptron dense neural network. So what we are doing is we are unsibling, that is, we are actually combining all these three models to predict whether the transaction is fraud or not. And I'm going to walk you through why I have used these three models and why I'm combining these three models together to get the best accuracy and results. So these are the inputs. I needed TensorFlow for deep learning, as well as I've enabled the GPUs, which we call it MPS on the Mac Metal for GPUs. Then these are the project settings. So this is the credit card CSV that I've downloaded local from Kaggle, and then this is the target column, which is fraud or not fraud, which we are trying to figure out. Um, and and these are the trailers. These are the trials that we are going to go through for all of these three models, and then the Ansible one, right? And then eager stop patience. These are the parameters that I'm going to walk you through as we go down into the other cells. At the end of the day, we are going at the end of this particular thing, we are going to save our model into this particular folder so that it can be reused later. So we are loading the data. So this is how the data looks like. This is the data size. It is 67 MB, which is not big. But once we are actually using neural networks, I know it gets really crazy, and it took me a lot of time to process everything. I'll walk you through that. So we have time, and then we have V1 to V28, which are the feature parameters which are masked. So the reason they are masked is because this is customer sensitive data and it is not exposed, but it is normalized and masked. And then this is the transaction amounts, all right? And then this is what we are trying to find out. We are trying to predict whether it is fraud or not fraud. Here you see everything zero because you would see eventually there are ones as well, but I'm just picking up the first five rows, so that's why you don't see it. And this is how our data type looks like, right? So most, like, everything is either int or float. There were some there was some cleaning done, so there were some duplicate rows which I have cleaned, and there are you know no crappy nans or something, so they were zero, so we are good with that. In terms of EDA, um, if you look at the data, we have a lot of non-frauds and very less frauds, of course, right? Because frauds are rare, and that's why you don't have evenly distributed data. So we have very imbalanced data set, which is good use case, right, for real world, but it actually puts us under a lot of pressure to do well in this particular model, because if the number of frauds and non-frauds were same, then the models would have done really well in predicting because it has a lot of data to support it, right? But that's not true with us. So these are the different feature sets we have, and most of them are normalized. If you see, the amount is not normalized, and a lot of outliers over here where some amounts are very far away, and most of them are saturated between 0 to like $1,000, right? Where most of the frauds have happened. In terms of collinearity, there are no features which are highly correlated, so we are good. For the VIF, the score is still fine. This amount looks a little bit higher, but we are still fine because amount is super important for us to have. So we are splitting the data over here as well as we are doing some feature engineering because as I've mentioned before, there are a lot of outliers over here that we need to, you know, kind of normalize. So what we are using is we are using standard scaler to actually remove some of the outliers and make everything normalized over our training data set. We are splitting our data set into training set data set and validation data set as also well as into test data set. Um, so so now we are why the reason is like why are we using XGBoost, Tabnet and multilayer Perceptron, right? Why are we using these three together? The reason is um, in the world of deep learning, tabular data, like the data which is in the CSV format or any relational database, let's say SQL or Postgres, these databases don't do well with deep learning inherently. For that, primarily, people still today in 2025 they are using traditional way of machine learning, but there are some breakthroughs recently happened uh, where Google has actually published this TabNet paper, which is attention-based deep tabular network. They published it in 2020, and then that's included into Tensor as well as into PyTorch, right? So we are going to leverage that, and then we are also going to leverage multi-layer Perceptron. So what we are trying to derive is, okay, fine, traditional machine learning tree-based XGBoost does really well as a standalone uh, uh, supervised learning, but if we combine them with deep learning, it's going to give us better results, and that's what I'm demonstrating it today. So, so our strategy is going to be, we are going to take all these three together and then do an Ansible that is combined together. Uh, and then we are going to see how we are going to do that later. So I'm going to explain this part later as we go through this particular process. These are just helper functions, right? So these are used generically throughout all the other cells. So I've just kept them over here. And then, we have started with XGBoost, right? With hyperparameter tuning and, where, we have these many parameters for XGBoost. And right, I'm tuning those hyperparameters over here. We are using uh, Optuna, which is kind of a library where you can actually create trials and studies to go through all these particular range of parameters, right? Let's say for estimator from 400 to 1400, it goes through multiple models and it does the fit test to figure out which ones parameters are actually giving you the best score, and then it returns you the best study over here once it goes through many studies. And that's where we had configured these particular parameters up there on how many trials we want to go through, right? So these are the parameters that will be actually configured on our second cell on the top. And then it gives you the best study, and then you actually on that particular best study you do a fit on the training data set and uh, get the and on the validation data set and get the threshold for that. So the things that the things that the things that we got over here is something like this, right? So when you plot that particular output, this is your best point, right? Where your precision and the recall at the highest point, and this is what you're looking at. So similarly with TabNet, you know, we did the hyperparameter tuning with the best parameter and did a fit on that. These are the different advantages of the TabNet in deep learning, and so they have these feature sets right? Again, you do a fit on the on those particular feature set and get the best and do the studies based on the trials, the number of trials that you have mentioned, like I've mentioned, and then you get the best F1 score for, like, try to get the best F1 score for that, uh, and try to predict that, and then you get these results, and this is how it looks like, right? So um, you could see that the first model did a little bit better, and this is kind of not doing so good, and you're getting the F score, which is which is a little bit lower, right? Than what it should be. Again, in terms of I did the same hypertuning parameter for multi-layer perceptron, right? Where you have these layers, right? Dense layers on the model, and then you're again, like, I'm doing the uh, study for that. I'm finding the best parameters, and then once you find the best parameter, you're trying to predict, and then whatever threshold and amounts you get, I did I did put it in here, right? So this is the best output, that probably this is the best point where I get a good precision and recall and F1 score. So ideally, what now we have to do is we have to actually combine this, ensemble all these three models together to get the best result through, right? So imagine this is like a stream of models together where you have your input coming through, and then you have like three models that the data has to go through to get an output. So again, doing the study on these different parameters. So this is our model one, this is our model two, this is our model three, right? We are taking this, and this is the weight. This is very important. Okay, so what is weight is, um, you have these three models, and these three models are giving you a certain F score, right? This model might give you a really good F score. Okay, so you need to make sure that the weight of this is more versus the weight of this and this particular model, right? And that's where you are actually, this is also your hyperparameter. And what you're trying to do is, based on these hyperparameters, you're trying to find the best F score, right? And that's what we want, right? We want to tune these parameters in such a way that I get a really high F score at the end of the day. And that's where this study is going through. So there are trials that goes through, and if you see, there are like trial one, trial two, trial three, all these trials, 45 trials to go through, and then we we got the results, right? So these were the results that we got. And I'm going to talk about those particular results right away. So so if you look at it, this is how the model, the study has actually differentiated the weights. Like, what the study is saying, and this is all about hyperparameter tuning, right? These weights, the number of this the what do you say, the the number, like 0. 0.6, that is the weight of W1, is not hard coded by me anywhere. It is just that the study and the hyperparameter tuning is coming up with these particular weights, considering that these particular weights are going to give them the best possible score for F1. So these are the studies versus the F1 score, right? So there are like around about these many studies that happened, and for each hyperparameter tuning, these were the F scores that these were the F scores that were best um, worked out to be, and that's what is returned to us. And then all we are doing is we are saving the entire model, right? We are saving the entire model in this particular folder, with so that it can be reloaded and reused later. So the conclusion of this particular study is, if you look at the the winner is like the combination of all these three models together gave us a really high F1 score. But if you look at the individual models together, it actually didn't give us, it did give us a decent F score, but actually this one actually did really win over the other models. And I think uh, doing this particular study was really important for me, especially because I come from banking and insurance domain where everything is in every form of data is in tabular data, right? And I have to do a lot of um machine learning around it is what I'm assuming once I get good at it. So yeah, thank you so much for listening. Have a nice day.